Welcome to my HPLC concept map. So we start with the legend. If you see this icon here, they represent various things in the concept map. For example, this gear here represents a mechanical parameter. So HPLC is actually a chemical analytical method that's used to separate a mixture of compounds. It depends on runtime. So runtime is the time taken for the last compound to be looped out from the system. They have to be as small as possible without compromising resolution. Resolution is actually the king in this HPLC analysis. It is described as how well two peaks are separated. It depends on various things, and it can be described by this equation here, a theoretical equation, and this is a practical equation. So like I compare resolution as a goal in a soccer match. So in a soccer match you have to score in order to win. Same thing for HPLC, you have to have resolution over 1.5 or equal to 1.5, otherwise you have to do the analysis again because your peaks are not separated. So another thing is back pressure. Back pressure is very important because back pressure determines the quality of the chromatogram. So for a HPLC system, the pressure should not exceed 4,000 psi. For a UPS system, the pressure can actually reach to 10,000 psi. So in case of a UPLC, we kill the back pressure. Now let's move to another thing, pigtailing. So pigtailing is another parameter of HPLC that we need to look at. So it's actually described as distance B being wider than distance A. You can see distance B here in this picture here, and this is distance A. And if the ratio of B over A is over 2, so that will be unacceptable. The peak will be unacceptable. But if it's between 1 to 1.2, they are acceptable. So sensitivity, and that is another HPLC parameter, is actually defined in terms of how much amount is actually detected. Let's just look at one by one. Resolution depends on selectivity. So selectivity, when you increase selectivity, you can see from this graph here, if you increase selectivity, you actually increase resolution as well. So it also depends on efficiency. So if you increase efficiency, you increase resolution according to this graph here. And final list for resolution, if retention factor is another thing that affects resolution. So if you increase resolution, if you increase K, you actually increase resolution. However, when you get a K over 5, it's not going to have any impact on resolution. You can see from this graph, this area, no matter how you increase, it's not going to have any effect on resolution. And let's just look one by one. Selectivity. Selectivity actually is how well the peaks are separated. It is not an indication of resolution, but it's an indication of separation of peaks. It depends on pH. So if you change pH, you're going to change selectivity. This can be seen by this obtained chromatogram. So you can see that the order of the peaks have changed here. That means selectivity has been changed. It can also depend on temperature. It can also you can see here when you have ambient temperature base 40 degrees, the order of the peak are different. Again, this shows that selectivity has been changed. So it can also depend on solvent type. Changing solvent type, for example, from methanol to ACN, will actually result in change selectivity. You can see these are the chromatogram obtained. You can see that Kofnak here being the last one, here being the second last, so the order of the peaks have changed. Ligand type is another thing that can affect selectivity. I can see here when you use this ligand here and here, which are different, you can see that peak 4 and 5, they are superimposed here when they are separated, so that means selectivity has changed. Also, percentage P is something else that can actually alter selectivity. In order to do that, you have to change K, and the change have to be disproportional. So now let's look at retention factor. Retention factor is actually mean of measuring the retention of compounds in the column. So if you have high value of K, it's actually signify that analyzed in the same path, high affinity to the stationary phase. You can change by changing percentage B or changing the ligand time. The percentage B, how does it change K? You can see here when we have percentage B of 50, K here is equal to 9.6. Here when you have percentage of 58, you can see 6.4. So from 9.6 to 6.4. Another thing, retention time again. Retention time actually can incorporate two things. TR is the time taken by the retained compound or analyzed, and unretention time, unretained time, which is actually the time taken by the unchanged compound, which actually move at the same speed as the mobile phase. So this is how K is calculated by taking TR minus T0 over T0. Now let's just look at efficiency. Efficiency actually measures the analyte as they are dispersed through the column. So we can be calculated using this equation here, and we have to can be actually calculated in terms of plate number, which we're gonna discuss later in this presentation. So you can see that efficiency is actually a pure mechanical parameter, can only be ordered by mechanical parameters such as flow rate, column length, and column diameter, and so forth. Column length have a very impact on efficiency. You can see here when we change the column length from 5 centimeters to 10 centimeters, here there is a change in number, theoretical number of plate. From here was from 3,999, where it went here for 8,197. So also HTP is another thing that in terms that affect resolution, that affect efficiency. So you can see that it relates to efficiency by this equation here, and the theoretical plate as can be utilized to validate the efficacy of the column inside. Once it falls under a certain value, you can change it because it's no longer doing what you intended it to do. It depends on longitudinal diffusion, mass transfer, and eddy diffusion via this equation, non-Van Meter equation. So look at the longitudinal diffusion. It's actually broad bending, which is caused by the dispersion of analyte molecule as they go through the column, because they have different gradient at that edge of the bend. To minimize it, you can use higher mobile flow rate or keep the tubing system short. Depends on linear velocity, and linear velocity itself depends on column diameter and flow rate. And now let's look at mass transfer. Mass transfer is actually mainly to the porousness of the stationary phase material. To minimize it, you can use more diameter stationary phase particles, use lower mobile phase flow rate, and it depends on core size. Another thing is eddy diffusion. Eddy diffusion actually is used to analyte having multiple paths. They can go in different paths as they go through the column, and to minimize it, you can have a well packed column. And the eddy diffusion is actually diffused as well if the flow is laminar or turbulent. Laminar is dead, sort of increase. Laminar tend to increase broader bond than turbulent flow. It depends on particle size. And let's just look at back pressure. Back pressure is another parameter, Hplc parameter. It depends on column length, particle size, and column length. So by this equation, we have this equation here where viscosity is this end here, and this end looking Greek word, not the Greek word, actually Greek letter, and here we have particle diameter and L's length. So also back pressure depends on linear velocity. You can see if you increase linear velocity, increase back pressure. It also depends on viscosity. So if viscosity change, then the back pressure will change. A less viscous fluid require less force pushed through it, ultimately reducing pressure. Sensitivity is another HPLC parameter, which depends on peak height, and peak height depends on percentage B. So if you increase percentage B, increase peak height, and also peak height depends on sample concentration. It also depends on the wavelength. And let's look at runtime, the time taken by the last compound to load out. It can be dependent on TG, which is the gradient time. So if you increase the gradient time, obviously it's going to increase the runtime. It depends on the column length. If you have long column length, obviously it's going to take longer. It also depends on linear velocity. If you push it quicker, you're going to have a shorter runtime. Let's look at peak tailing. Peak tailing can be caused by pH. pH, pH alter the physical properties of, not really change the physical properties of analytes. Sometimes they're ionized or non-ionized. This will determine how long they're going to stay in the column and probably lead to peak tailing. A ligand type as well. So different ligand type behave differently. So they can either cause the compound to stay longer in the column, shorter. So the other thing that you need to think of is end capping. End capping, you have if the surface of the silica is not end capped, the silica may interact with the function protein in the analyte compound, and this can lead to tailing. Another one is carbon load. Depends on how carbon we have. Carbon load increase ligand density, and in this case, it's going to increase the number of free silanol and ultimately reducing peak tailing. And last but not least, metal ions in the silica may actually interact with analyte, and if that happens, they will be retained longer and lead to peak tailing. And finally, let's just look at AUC, area under the curve. It depends on peak width, and peak width itself depends on percentage V. So if you increase percentage V, it actually lead to a decrease in width, and width also depends on injection volume. So let's just look at it because there's something special about area under the curve. So for the area under the curve, if you increase percentage B, you actually decrease width. And here, and see if you increase percentage B, you increase height. So overall, we can say that the AUC is not affected by an increase in percentage B. That's a take-home message, and thank you for listening. I hope